Good morning, students. Today we shall be doing an introductory lecture on tensors. This tensor we shall be needing this tensor in relativistic quantum mechanics. This is the second lecture. And one thing I told you in the last class that keeping this in mind when we shall be doing with Greek indices. We shall be taking three space and one time, and we shall be taking Latin indices. We shall be taking only space. But in this lecture we shall not keep any restrictions as such. We will treat the space coordinate as xi, and this is a n-dimensional space. So the coordinate will run from 1 to n. Say there may be space, there may be space and time. So it's not a problem, but we will take this as a single coordinate and we will do the algebra accordingly. So this is a general lecture on tensors. Okay. So this is one, right? So this is the label. This is the coordinate, and the set is the label for that physical point. If the space is n-dimensional, so to coordinatize the n-dimensional space, you need to have a unique label for this unique label for every physical point. Right, in Cartesian coordinates that uniqueness is there, but in spherical polar coordinates you know that the reference axis, this reference axis, suppose I am embedding a sphere on the Cartesian coordinate system, so x, y and z, and any coordinate, suppose on the sphere or wherever it is, anywhere in space, that can be coordinatized by r theta phi. So if we drop a perpendicular here, if we join this is phi, this is r, and this is theta. So we know these things. Suppose this is the physical point P. Now this point P is also labeled by x, y, z. Where it is, you drop a perpendicular here, you drop a perpendicular there. So this is x, this is y, and if you drop a perpendicular on the z axis, this is z. So this physical point P is labeled by r theta phi. This physical point P can be labeled by x, y, z, and there is a transformation between these two coordinates. That transformation is very important, that we shall be doing. When you can consider this r theta phi as x1, x2 and x3, and consider this xyz as x1 prime, x2 prime and x3 prime. So the same physical point P can be represented by this and can be represented by this level. So, but there will be a transformation from this coordinate to this coordinate, from the unprime coordinate to the prime coordinate. Any one you can choose. You can choose this as unprime, this is prime, this is unprime, this is prime. It's not a problem. We'll have the transformation. Okay, that we shall be doing. But the important thing is what I was talking about. In Cartesian coordinates, this xyz is the label, and this label can be used for the whole space. But see, if we take this spherical polar coordinate and come here, suppose on this reference axis, this z axis, what's the value of r? Value of r is this. Suppose the point P comes here. The point P comes here. Acha, let's see first for the what will be the value of the Cartesian coordinates. X will be 0, y will be 0, so 0, 0 and z. Fine, and this level is unique. But if we go for this Cartesian coordinates, spherical polar coordinates, this distance is r, right? So this level is r. Theta will be 0 naturally, because this will close. This will come to this line. Theta will be 0. But what is phi? The problem with phi is phi can be anything. Phi can be anything. So this line is not coordinatized in spherical polar coordinates. We have a lot of advantage with spherical polar coordinates. The spherical symmetry, we exploit the spherical symmetry using spherical polar coordinates, but there is a problem. Remember, this line is not coordinatized. This line is not uniquely labeled. I can uniquely label this line with Cartesian, but I cannot uniquely label this z-axis with spherical. Phi is anything. R is this distance, this z distance. Theta is 0, but phi is anything. So the important thing is this labels which I shall be using for the n-dimensional space. Here it is 3-dimensional. I can't draw n-dimensional space. This label is a unique label for every point, and you shall be having another label as x prime I for the same physical point, and these two labels or these two coordinates are uniquely defined. You have the whatever the n numbers you have. Here is also the same n-dimensional space. Means in this case, in case of xi, it is x1 to xn. X prime I, it is x prime 1 to x prime n, and this set is uniquely defined. This set is uniquely defined, not like this, not like phi is anything. No, it has to be uniquely defined, and we will have transformation between these two coordinates. Okay, fine. So this is one. Now there are a few things which I need to say. The coordinates will be labeled with a superscript. But there will be subscript as well. You will have vectors. Suppose AI, this is a covariant vector. Why it is called a covariant vector, I shall come. This is a subscript and this is a superscript. Do keep one thing in mind. Keep this position open. Suppose if I want to go up and J wants to come down, it must have that option. Don't write like this, one on top of the other. Have a practice in writing in this fashion. Keep that position open. If I wants to go up, this is a mixed tensor of rank 2, one co, one contra. I'll come. Now if I wants to go up, it should go in that position. So keep that thing in mind. Okay, so this is a subscript, this is a superscript, and there is another thing which I'll be using too much. You have done this in your BSc, the Einstein summation convention. So let me tell these things one after the other. Einstein's summation convention. Suppose if you have a repeated index, in case of tensors, if you have one index will be a subscript, the other one will be a superscript. Suppose if it is like this, AI, BI, if it is like this and you have these two indexes in common, there will be an automatic sum over this pair of index, and this is called a dummy index. Dummy index. Okay, so this is a vector, this is a covariant vector, this is a contravariant vector. Now this is a dummy index, AIJ, AII. Now if you have something like this, suppose this is a tensor Tij, and you sum this with a tensor of Ik, what will be the resultant tensor? See here, the dummy index is I, and J and K are free indices, there is no sum. So the resultant tensor will be some tensor, say Q, will have a superscript J and a subscript K, and the positions must be left intact so that they can go up and come down. Okay, and I am talking of Einstein summation convention. This sum is implied. If you have a repeated index, this I, the sigma is implied, so I don't need to write that sum. Fine, and these are free indices. Clear? Okay, so these are free indices. Now let's go into another thing. I was talking about coordinates. Now suppose I have a set of coordinates. I have a set of coordinates x, y, z, and naturally these coordinates are independent. I take a set of coordinates such that these coordinates are independent. So n dimensional space, n coordinates. So if these coordinates are independent, if I take a derivative of that coordinate with respect to the other coordinate, it will vanish unless and until the coordinates are same, right? So let me write that. So let me write that. Suppose xi is one coordinate. Now if I take a derivative of this coordinate with respect to some other coordinate, I not equal to j, I not equal to j, so this will be 0 for I not equal to j. Only this will be only 1 if I equals to j, that means if the coordinates are same. So then what does this stand for? So this implies del xi del xj is Kronecker delta. C should be Kronecker delta. Do one thing, keep this in mind, keep this I index on top and j down. I have a habit of writing this I and j, not one on top of the other. So you also better develop this habit. So this is Kronecker delta, right? Now there is another thing. Which I'll be doing is derivative of a scalar field. Derivative of a scalar field. Suppose phi is a scalar field, and which is a function of xi's. Now if you take d phi dt, how shall you write this d phi dt? So that will be del phi del xi dxi dt sum over I, right? What it should be. So it is, if you expand this as del phi del x1 dx1 dt plus del phi del x2 dx2 dt. Del phi del xn dxn dt. It is actually like this, right? So you can represent it like this, and naturally this sum will not be there. So in short you can write it like this: del phi del xi dxi dt. You can write this as well: del phi del xi xi dot. Clear? The xi dt is time derivative, so xi dot. Now this is the time derivative of a scalar field. Now if I take a space derivative of a scalar field, how shall it be? How shall it look like? Let's do that. You have a scalar field. Okay. Now try to realize this. You have a space. Suppose this is the point. This is the physical point where it is level with xi. The same physical point is level with xi prime. So if it is a scalar field, that means it must be the same, right? What is a scalar? If you transform the coordinates, scalar doesn't change. Suppose you have a temperature at a particular point, or the luminance at a particular point, right? So that point, whether you represent it by Cartesian coordinate, represent by spherical polar coordinate, the luminance doesn't change or the temperature doesn't change. So phi is a scalar field. If it is a normal pressure is a tensor quantity. I am talking of particular pressure in a particular direction. If you choose the direction, then it becomes a scalar. In general, pressure is a tensor quantity. So at that point, the pressure remains the same whether you take it, or I'm talking of normal pressure. Normal pressure remains the same if you take it in spherical coordinates or in Cartesian coordinates. So it's not a problem. So if you take a derivative, suppose del phi del x prime I am taking this derivative of phi with respect to prime coordinates. So what will be? This is del phi del x I del x I, sorry, it should be some other dummy index, j, it is j del x prime I, right. Now bring this in front, del x j del x prime I times del phi del xj. Okay, now see, what is this? This is a field, right? This is a field. It's a gradient of a scalar field. Gradient of a scalar field. Oh, this is a vector field. So vector field transforms from one coordinate to the other coordinate, and the rule of transformation is this. The rule of transformation is this. Now if you say that del phi del xi is vi, and del phi del x prime I is v prime I. If I plug in these values, what shall I get? This is v prime I is equal to del x j del x prime I del x j del x prime I. This is v j, right? So here I have taken I, so this is I. You have taken I, so this is I. If I take j, this will be j. This is the whatever free index I am taking here, it will appear here. Here this is del phi del x j, that means this is j. So naturally this will be j. That's what I have written. So the vector field transform like this, right? What's this rule of transformation? This rule is a rule for transformation of a covariant vector. This vi is a covariant vector. That means a vector which transform like this. If this is the rule of transformation, this vector is a covariant vector. Clear? Then, so a covariant vector transforms like a vector field. Then what's a contravariant vector? Okay, first take note of this. Okay, this is a covariant vector. Achha, then what's a contravariant vector? This xi, this is a label, this is not a vector. But if I take change in xi, it's a displacement. Displacement is a contravariant vector. How does that change? Let's see that. Suppose dxi or dx prime I. This dx prime I change like this. Del x prime j del x prime I del x j dxj. Right. You are identifying this statement. What is this? Suppose x prime I. Suppose you have a patch like I have a space here. Okay. Now this same physical point P is represented by x prime I, means x1, x2, x3, x4 dot x prime 1, x prime 2, x prime 3 dot 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 x prime n, and this same physical point is represented by unprime coordinate. Think that point. One is represented by xyz, the other is represented by r theta phi. I am talking that part of the space where you have the option to label that point uniquely. That label is unique, r theta phi. So that is coordinatization. That part of the space where it is coordinatized. So this thing, suppose prime is r theta phi and x is this this x i's are xyz. So if every x will have a transformation rule, what is between spherical and Cartesian. So it's r sine theta cos phi, that is what? That is x. What is y? R sine theta sine phi. What is z? R cos theta. I'm just giving an example. Suppose these are xi's and this is x prime i's. So this is the transformation rule. So every xi will be a function of x prime I, and you will have the reverse as well. You can choose this as prime, this as unprime. It's not a problem at all. This is not a problem at all. You will have the reverse relation as well. You can have the reverse relation. You know these things. So this x prime I will be a function of x i's, right? Or you better write it like this. The x primes will be, each x prime will be a function of x i's. Now if I take a derivative of this, or better write in this way. Xi is a function of x. X means all x, means all unprime coordinates. Now if we take a derivative of this, what will be? Xi. That is, by rule of calculus, del x I del x prime I del xj dxj, or better write it in better expand it first. 1, this is I, this is 1, this is 1, right, plus del x prime I del x2 dx2. Del x prime I del x n dxn. Now see, if we are transforming from xyz to r theta phi, then i's will be from 1 to n. You suppose you choose r here, only r, then what will be, I am saying that only r, you want to get r in terms of x, y and z, and suppose this x prime I, when it's x prime 1, this is r, when it's x prime 2, this is theta, when it's x prime 3, this is phi, and when it's x1, this is x, when it's x2, this is y, when it's x3, this is z. Fine. Now, so what will be dx1? So dx prime 1. If this is 1, this I is the free index. I is the free index. See what I have written. I have just expanded this sum. This j is the dummy index. J goes from 1 to n. So if you will be choosing every I. When I is equals to 1, this is dx1. So then it will be del x prime 1 dx1 plus del x prime 1, this I will be always 1, dx2 plus, you just carry on, del x prime 1 del x n dx n. In case of these things, you will be restricted to del x prime 1 del x 3 dx3. Fine. Now if this is r, this is r, so this will be dr, right? This will be dr, and then will be del r del x dx plus del r del y dy plus del r del z dz. This is the transformation. This is for the dr. You will have for the d phi. You will have for the d theta. Right? You can have the other way around as well. Suppose you choose this unprimed as this x1 as, let me write it here first. You will have this d theta, then del theta del x dx plus del theta del y dy del z dz. D phi, it will be having del phi del x dx plus del phi del y dy plus del phi del z dz. Here, this is the relation. Then for free index I is 1, 2, 3, you will having this relation. You can have just the other ways around. It's very, you can choose this prime as x y z. So this is 2, this is y, this is x prime 3, this is z, and this is unprimed as r theta phi. Okay, then what will be the relation? Let's write that. This very symmetrical. This will be x. So let me write it. I'm expanding this relation. So this is dx is equals to del x del r dr plus del x del theta d theta plus del x del phi d phi. This is the relation. So you can go from this dx, dy, dz with coefficients like these to dr, and you can go from this dr, d theta, d phi to dx. Okay, I think you got it. This is dy is dy dr plus dy d theta plus dy d phi del phi d phi. Then this is I must fill this up. Now the vectors, if I displacement, this is a vector. The vectors which transform in this fashion are contravariant vectors. So if the rule of transformation is this, if you have a coefficient like this in front and this is a vector, if this is a vector, so this is a contravariant vector. So suppose a vector ai del x prime I del x j a j. So this is a contravariant vector. And what is a covariant vector? Which transforms like a vector field, right? So I think you remember the index will be below. So this is del x, I is here, this is the free index, here I is the free index. So del x del x prime I del x j bj. So this is the covariant vector. What we are doing, we are transforming the vector from one representation, means which is represented in the unprimed coordinates, to the prime coordinates for the same physical point. That is very important. For same physical point P is represented by the prime coordinates and it is represented by the unprimed coordinates. We are transforming the vector from one coordinate system to the other. If the rule of transformation is this, the coefficients are this, it sits in front of the vector, this is a covariant vector. And if the coefficients are this, it sits in front of the vector to get this vector, this is a contravariant vector. Okay, I need to fill this up. Let me pause the video first. Okay, now let's see the contraction. So this is a contravariant vector, this is a covariant vector. If you contract them, what happens? See, contravariant tensor is a tensor or contravariant vector, rather tensor of rank 1 is a vector which transforms like the displacement, right? And covariant vector transforms like the field. Contraction is basically a dot product. For example, suppose if f dot dr, what is this? This is a work done, right? dw, and this dw is a scalar quantity. You know that work done is a scalar quantity. So dot product basically is a scalar quantity. It's index free. scalar is index free, that means it is independent of, when it doesn't transform, if the coordinates are changed, it remains invariant under coordinate transformation. So if I contract these two, this is some sort of a displacement, suppose AI dot or A prime I dot V prime I. This should be a scalar quantity. So how shall I contract these two? This should be invariant, means it is whatever it is in a unprimed frame, it will be same as in a prime frame. This is actually this, I am writing it prime, it's basically A prime I, it is means this is a function of prime coordinates, that's what it represents. And say prime I is basically this. Also V prime I and if it is unprimed, got it? So if I contract these two, what will happen? This is a contraction, this is the inner product, it is summed over I, no free index, I is a dummy index. First write this, del x prime I, del x j, aj, okay. Now I need to write this. Can I write this directly? What's the problem? See, if I write this, here the index is j as well, the dummy index is j as well. I can't have two pairs of same dummy indices. Why? Because we will not get the cross term then. So I have to change the dummy index. You can change it to anything, it doesn't matter, it will not appear on the left hand side. So this should be del x prime, suppose I am taking k, del x prime I vk. Now this is what? This is del x prime I del x j del x prime there shouldn't be prime here, we shouldn't have a prime here. So this is del x k del x prime I aj vk. These are numbers you can commute. That's one of the greatest advantage using tensors. Basically, this is basically a 2x2 matrix. This is also a 2x2 matrix. You can write this is in the front and this is later. It's not a problem because these are numbers, these are matrix elements. Okay. Now this will be, by the language of calculus, naturally it's summed over I. So this will be what? Del x k del x j aj vk. Now this is what? This is delta kj. This is a Kronecker delta, because unless and until k equal to j, this will be 0. Only it will be 1 if k is equal to j. So this will be delta kj. Remember, I am not writing one on top of the other. I have a habit of doing this. You can't write, if it is a tensor, So you better not write one on top of the other. You must have some space. So this can go up, this can come down. You must leave this space. This space is reserved for J. This space is reserved for K. Okay. AJ, VK. So this gets contracted. So that's AK, VK. Now, so this K is a dummy index. You can change it to I. It doesn't matter at all. So that's AI, VI. So whatever you have in the prime frame, you're having the same thing in the unprimed frame. So it is invariant under. So this is invariant under this coordinates transformation. If you go, since this is a scalar, but this remains invariant under coordinate transformation from x prime frame to the prime frame, unprimed frame. Okay. Let's check this. This is very important. And okay. There are few problems. We shall be doing few little problems then. To understand what is what. This is a scalar. If we have a tensor like this, let me define few things. Suppose this is a contravariant vector, this is a contravariant vector. Now what I want is I want to show that the derivative of this doesn't transform as a tensor. Can you show this? Let's see. Show that. So this is a problem. Show that del A prime I del x prime j does not transform as a tensor. How can you show this? Let's do it. Del solution A prime I del x j is equals to, I can write it like this, del prime x j. And so what is A prime I? A prime I is this, del x prime I del x. You must change the dummy index. This j is already free index taken here on the left hand side, so you can't have a dummy index j, so take it as k ak. Now take the derivative. See, del 2 x prime I del x prime j del x k ak plus, just one thing, del x prime I del x k del ak del x prime j. See, this, if I have only this term, then this part, suppose this term is not there, this part transforms as a tensor, right? But this part disturbs the structure. So due to presence of this part, this thing does not transform as a tensor. So ordinary derivative do not transform as a tensor. If you go to GR, you will see that the covariant derivative transforms as a tensor, but this is the ordinary derivative. This doesn't transform as a tensor. Okay. So due to this part, this term this part ordinary derivative do not transform as a tensor. See, check this. Okay. There is so contraction done. So let me tell you something about the rank. These are all tensor of rank 1, that's vector. Let me go into tensor of rank 2. So tensors of rank 2. So how does they transform? Transformation of tensor of rank 2. Now suppose Tij, you can Tij prime, so it's in prime coordinates, you can write it as a product of two vectors, A prime I, B prime J. So this is a contravariant tensor of rank 2. Now how does this transform? This transforms as A del x prime I del x k. You can't use j, j is a free index, ak. Then this will be del x prime j del x l bl. So this will be del x prime I del x k del x prime j del x l ak bl. So this will be t kl. I can write this. So del x prime I del x k del x prime j del x l t k l. Okay. So this covariant tensor of rank 2 transforms like this. So if you have a transformation coefficient like this, then it is a, sorry, not this is a contravariant tensor of rank 2. Now if it is a covariant tensor, suppose if this is a covariant tensor, then what will happen? This is a covariant. Suppose Tij, and suppose this is some different, I can write it as a product of two tensors. Suppose this Vi prime Ui Uj. Prime. So what's the transformation for this? Del x prime I del x k vk. I can't use j because j is already a free index I am using. Now this will be del x, uj will be del x L del x prime j ul. So del x k del x prime I del x L del x prime j vk ul. Says if this is, let's take it a different thing. T S ij prime. Sij prime is this. So if Sij prime is this will be Sij. Del x k del x prime I del x L del x j skl. Fine. So if something transforms like this is a covariant tensor of rank 2. Let me do the mixed tensor as well. Transformation of the mixed tensor. Suppose mixed tensor, since it's a mixed tensor, let's write it as Mij prime. So this is a mixed tensor, one rank co, mixed tensor of rank 2, one contra, one co, one contra, one co. So so this is AI prime and this is Vj prime. I can take a mixed tensor as a product of two vectors. I think you have known dyadics, something like that. So what's the transformation for this? Del x prime I del x k ak, then del x prime j l vl. Okay, this is the transformation for the co, this is the transformation for the contra. Now take these to front, you can easily bring, these are numbers, that's the greatest advantage. You can swap, these are numbers. What is this? Yeah, this is this. Del x prime I, del x k, del x l, del x prime j, and this is mkl. Say this is a mixed tensor of rank 2, one contra, one co. If the transformation is like this, if this is the transformation coefficient, then this is a mixed tensor of rank 2. So you can have any tensor. Suppose mixed tensor of rank 3, 1 co, 2 contra, you write it as a product of vectors, dyadic form. Then you write the independent transformations. Then you choose the transformation coefficients on the left hand side and the vectors on the other side. The remaining vector will look like the tensor on the left hand side. It's very similar. It's like this tensor on the left hand side. Then you write the tensor and you get the resulting transformation equation. So that's it. And Kronecker delta, you know that it's a mixed tensor of rank 2, 1 co, 1 contra. So in a three-dimensional space, normally co and contra is the same, so I'll do few things in general. Let me write a general thing. General thing I think you will be able to write. I'm not going into rank 3, rank 4, rank 5. It's very similar. You write in the product of matrix vectors in the dyadic form and then you write it. Okay. So anything I have not touched as yet. Contraction I have done, inner product I have done. Let me say one thing. Any tensor can be represent as a sum of symmetric tensor and antisymmetric tensor. Suppose it's like this. Suppose any tensor Tij, this tensor is a covariant tensor of rank 2, and this can be represented by a symmetric tensor plus a antisymmetric tensor or a skew symmetric tensor. This is possible. You can write it. So this is a tensor, this is a symmetric, this is possible. Symmetric tensor means, what's a symmetric tensor? This is a symmetric tensor. Symmetric tensor. This is a antisymmetric tensor. This is a symmetric tensor, this is an antisymmetric tensor. Symmetric tensor means Sij is equals to Sji. Very similar to the eta mu nu. Eta mu nu is a symmetric tensor. So this eta nu mu. If you swap the indices, no sign change. And here it is antisymmetric or skew symmetric is minus AJI. It is always true. This is true for any matrix as well. You know that you take any matrix which is an asymmetric matrix that can be represented as a sum of a symmetric matrix plus a antisymmetric matrix. Just a little digress. Can you tell me the number of independent components of a symmetric matrix? Independent components of a symmetric matrix. Let's do this a little bit. Then you will understand the number of independent components will remain the same. Achha. So, suppose a tensor of rank 2 can be represented as a matrix. G mu nu or eta mu nu is a matrix. It is a tensor of rank 2. Suppose number of independent components of a symmetric matrix. Suppose this is an n cross n matrix. So n rows and n columns. How can you get the number of independent components? It is basically the diagonal plus one side of the diagonal. So the total number is n square, right? So what's the number of components in the diagonal? N. Just subtract that. So you take the diagonal off, then you take 1/2 of the triangle, one triangle, so divide by 2. So you take this part of this. But you need to add this diagonal, right? So plus n. So this is the number of independent components of the symmetric matrix. And number of independent components of antisymmetric matrix how much? Number of independent components of an antisymmetric matrix. Can you just tell me? N square minus n. You take the diagonal off because the diagonal elements of an antisymmetric matrix is 0. Divide by 2. Yeah. Now, so basically what I say is, basically at any tensor, I just told you, Tij is sum of a symmetric matrix plus a antisymmetric matrix. So what is the number of independent components of any tensor, any asymmetric tensor or asymmetric matrix of rank 2? N square. So if I add these two, n square should come. Right, if I add them, so add them, since Tij is equals to Sij plus Aij, if I add them, I'm doing on the left hand side, this total should come as n square, means the total number of elements, n cross n. So that's n square minus n by 2 plus n square minus n by 2. So this plus this is n square minus n, right? Plus n. So that's n square. So it matches. Fine. So I think we have done a little bit on tensors. Maybe something is left over. You shall point me. I'll do it in my next lecture. I shall prescribe you to deduce those vector identities which you have done in this BSc class using tensors. I show you one. You will do the rest. Suppose I show you one, you will do the rest. Okay. Use this symmetric properties, use this antisymmetric property, then you will be able to do it. Suppose use this del cross P. If P is a vector, as far as three-dimensional space is concerned, covariant and contravariant is the same. Is basically, if you take the ith component of this is an epsilon I j k del j is del xj pk. Okay, del xj is acha. Now tell me, let's do a very simple. What is del dot P cross Q? What is the identity? How can you prove this? How can you prove? Using tensors. Very simple. See, this is basically a scalar. So this is independent of any index. So if I write it in this index form, what shall it will be? This del dot, suppose this is del I, right? And P cross Q is epsilon. This is a vector which must return a free index I, that should dotted with this. Then you will get the dot product. Means suppose del I pi. What is this? This is basically del dot p, right? So think this as a vector. This as a vector means this P cross Q is as if P. So this index is, this has a free index I. So this must return a free index I which is dotted with delta I to give a divergence. So let me write it. I j k del j, not del j, sorry, pj qk. Okay. So the epsilons are, you know, epsilon is completely antisymmetric tensors. You tell me in the next class, just I shall ask you how many independent components of there is in epsilon. Technically, it is in three-dimensional space. We are doing in three-dimensional space now. So if number of components should be 27, right? 3 cross 3 cross 3. 3 indices are there. So this is a rank 3 complete antisymmetric tensor, covariant. And we are contracting in covariant structure because we are doing in ordinary three-dimensional space. So their covariant and contravariant is the same. Ordinary in three-dimensional space. Achha. Let's take this out. I j k del j. Oh, sorry, del I pj qk. Whenever you write some expression like this, you must check whether all the pair, the dummy index must come in pair. See, I, j, j, k, k. Now, epsilon I, j, k. This is pj del I qk plus qk del I pj. These are components you can swap. That's the advantage. Now, here you can bring pj's in front. Pj epsilon I j k del I qk plus bring qk front, pass epsilon I j k del I pj. Now this is what I have made some mistake, I think. No, this I and this is k, so I should come in the second position. How it is defined? This ith component, I should come in the first position. j k, it should be like this. So here I and k, so you must swap these two. So since this is a completely antisymmetric tensor, if you swap two indices, you get a negative sign. So pj epsilon j I k del I qk plus, again you must bring k front. See, I and j. If you k front means you are operating cyclically or two permutations, so that shouldn't give any. So two minus signs, so that will give a plus sign. So qk epsilon k ij del I pj. Now this is what? This is minus pj. This is basically del cross q and the component will be j. This jth component del cross q, this part, plus qk you take, this is del cross p, and the component will be kth component. So this is what? The dot product, the divergence of, right? So this is negative, this is positive. Let's write this first. Okay, write this first. So del dot. Why I am writing del? Just wait. This is okay, this is okay, this is okay. No, it's okay. Oh, here. P dot del cross q plus q dot del cross p. Okay, so this is, you can write this in front, it's not a problem. Q dot del cross p minus p dot del cross q. So this is the identity. You must try all the identities which you have done in your BSc using this matrix. I shall make a list of videos for that, but you better try it first. Okay, so thank you very much.